So hi everyone, welcome to the second part of this tutorial, quantum machine learning for speech and language processing. So for my part, there'll be application and some practice feeling when we do this kind of research related to quantum machine learning. So before I start my talk, I want to give an overview about quantum machine learning as a solution from 2018 to 2023. So if you look like this diagram, we can find out mostly consider a speech recognition task from CTC to RN transducer and the joint supervised and unsupervised ASR like just. So we can see there is performance boosting, right, like year by year. So right now we take advantage from this DNN-based architecture. But meanwhile, if we look at this figure, on the orthogonal of this axis, we also have some kind of characteristics driven task. For example, we want to reduce time capacity, sample capacity, improve data encryption, and somehow improve security issues. So I would say some of the work is trying to addressing these issues not come from one orthogonal like result, trying to combine some quantum property. For example, like our work in ICAS 2021, we use a quantum encoder, but that encoder is in a separate machine. And to do this data isolation and trying to improve some security condition. And in the CVPR 2022, there's another paper like simulate image patches as a token with a weight function that outperform the swing transformer. So I would say this kind of research got this inspiration from quantum, but the model is not fully quantum machine learning based model. But we can see by incorporating a little bit about this quantum property, like our model can get both have improvement on the performance driven task and also adding some ingredient on some special using condition. But meanwhile, I would say if you coming from a quantum computing community, the main challenge and the big challenge you want to resolve is still more fundamental. For example, we do know before 2000s, there's in 19s, there's some original paper describe how to use quantum algorithm to classify phoneme. And more recently, in Google, they have a quantum supremacy paper. So for those models, they are purely quantum, and the problem they're gonna tackle is like is hard to resolve on the acoustic machine. So in this way, this push the horizon about the task we can resolve. So now we can, when we look at this solution, we can actually when we mention quantum machine learning, which is take advantage quantum computing. Right now, due to the hardware constraint, we could not directly do those problems like the red dots, like the purely quantum circuit or quantum kernel things. But meanwhile, the hardware like revolution is pretty fast. Like you can think about like a decade ago when people working on DNN, so we can actually do some pioneer work trying to combine these things together. So for today's talk, I will give some recent example how and where people can conduct research. I mean, like if we consider as a researcher, we want to step in this new quantum machine learning community or trying to doing some quantum machine learning application, I would say right now it's not purely performance driven task. For example, if you really want to use a pure quantum model, the thing you can deal with is actually molecular data and some quantum format data, which is a popular track in Neurisk and ISML since this year. As a speech researcher, right now, we are focused on production-driven task. So I would say here is something we should focus and look at doing today's talk. So again, I want to mention some fundamental question. So why should we do quantum machine learning research? Let's say maybe next year. So I would say we're trying to resolve some question that cannot be done with classic CPU. For example, with quantum machine and quantum simulate QPU, we can actually dealing with the data with complex phase information, and we can process this quantum format data directly. And the second thing why we do this kind of research like is we're trying to incorporate this quantum property into deep learning solution. That's, for example, I say, by using quantum machine, you projecting those features in a high-dimensional hyperparticle, so you can have a better representation power when you separate those features, and you can do the encryption and data isolation, which could not be done with the acoustic algorithm. And another question, I would say a lot of researchers are interested, maybe mostly today, is how can we do quantum machine learning in 2023? I would say mostly there is some CPU-based QPU simulation. Right now, actually, there is a TensorFlow quantum package, which you can directly do some quantum circuit training and even train with means with your quantum-based model directly. And meanwhile, there's also a PyTorch based solution called Pennyline. I would say you can first use a CPU-based QPU simulation for your work. And also they have TPU-based simulation. For example, you have ASIC, which trying to accelerate this tensor computation progress when you do this quantum simulation. Finally, for the real application, there will be Q-ski and BNQ. That is for the real quantum machine. So I hope if you get nothing from this tutorial, these 2 pages help you understand what kind of research we can do and what the thing we're going to talk in the following maybe 1 hour. All right, so as an example, I'm saying, okay, so there is some preliminary work. How this work look like? So I would say right now, in recent 2 years, quantum mainly be considered as a feature extraction for both acoustic and language information. For example, you project those acoustic feature and language embedding the latent space, and then by having this projection, people find out, okay, there is some slight improvement when you certainly mapping back this feature with your acoustic classification algorithm. I will talk about this detail, but it's one kind of main category. And also there's a quantum as hyper plane modeling for kernel learning. Right now, there's one paper for speech recognition just released today. Is one of my side project when I was interning Google. So we find out, okay, with quantum kernel learning, we can do this kind of separation for low resource language. And also, thank you, my advisor, Professor Lee, we do this kind of research. And the third part is another thing right now is adding some nonlinearity for hyper quantum acoustic modeling. I would say quantum is a tool when we mapping this data in the high dimension space and mapping back. But meanwhile, there's some recent discussion saying, okay, this mapping is actually don't have this kind of nonlinear transform. So there's some paper just discussion these issues, like June's discussion and one paper in NeurIPS last year. So I would say these 3 kind of main category way you can do this kind of research. So the first one is kind of low-hanging fruit, and the following 2 is much fundamental. I'm going to review that. All right. So in this 1 hour, so first I will talk about the background about quantum computing and why did quantum computing motivate us to kind of revolutionize our new design for machine learning. And the second, we're going to talk about quantum machine learning through a perspective of representation learning. And finally, I will provide some little bit implementation saying how we can implement those hybrid quantum machine learning as a part of this tutorial. So I would say, since we still have time, so if you have questions, you can leave your question in the chat room, and I will try to answer that even after this tutorial. Okay, so let's go to the first part. So the background would say what kind of data and algorithm we are looking today. So when we talk about quantum machine learning, there are actually different diagram we can look at. For example, the data can be quantum like this, but the algorithm can be also quantum. And for the acoustic algorithm, we're gonna dealing with is actually the data is a acoustic format. Acoustic format means like 0 and 1, and in the bit format, and algorithm is also in the bit format. And for the red one, you can think of some physical data have to use some specific like high dimension methods you're dealing with. But we also look at today is actually the data is quantum, and people use some acoustic algorithm like DNN now to dealing with this black hole data. That's one example. But what we look at today is we have some acoustic data like speech and language corpus, but can we use some quantum algorithm to dealing with this acoustic data? So they have some advantage. For example, we can have some quantum speed up and large repetition space and memory and model capacity advantage depends on how you design and select your hardware. But also we also have some disadvantage. So one well-known disadvantage is some of the quantum hardware is not really ready yet. So once you're doing the simulation, the result is really good. But when you apply the real quantum machine and the quantum qubit larger than 30 qubits, the performance will have a lot of sensitivity issues and large error bar. So I will cover these issues later. But as some advantage we look at mainly today is for the large representation space and some potential like hyper computation architecture, which can be good for speech and language processing. Let's say what is quantum exactly? So when we look at a vector, we can find out in the quantum space there's a Bosch vector. So which is you consider a qubit between 0 and 1, chi 0 and chi 1, and there is some probability density between these four, and you will only have your actual value once you're doing the measurement. So the background is while these things can actually speed our acoustic computation. But it is a paper called Quantum Machine Learning in Nature 2017. What these things have a good summary is by incorporating a fully quantum machine learning. So in doing this update process, they will have some speed up. For example, when we consider MTT application, HACL algorithm, so this is used to be serving linear system and the quantum random access memory. So this is related to how you select your QPU. And we can find out you can do different things with a purely quantum algorithm. For example, Bayesian inference, online perception, least square fitting, acoustic, like Boltzmann machine, quantum PCA, quantum SVN, and quantum reinforced learning. So they will actually have some speed up based on this algorithm design inside this quantum random access memory. But today we more coming from the algorithm perspective, but here just give you a taste saying, okay, even those classical algorithm can have a quadratic speed up with the simple size of n. So why especially today this quantum machine learning become a hot topic instead of research project or something working in the future? We can look at a figure like here. So this figure is sourcing from a 2016 paper in International Conference on Computing Frontier. So in this paper, they expect there's a convergence between this quantum software and the quantum hardware. So what this convergence means, like, for example, when the hardware is little processed, we couldn't really do a real algorithm based on this only simulated results. And then expect around 2025, you can actually have a Q acceleration with those kind of quantum rows on the machine. And eventually become converged around 2013. So right now, I think we are around here, and no matter what we are listening today with this kind of interest, you're actually in a really pioneer stage. So the open question could be, okay, since we expect they all be converging one day, but when these things can actually converge, do we have some data point to support these things if we want to initiate this kind of research? So here are some data points saying how recent the qubit is actually become large and accessible for the commercial level and even for some school level. So when we look at this qubit, I mean, the quantum computer in 1998, there's only 2 computable qubit in the machine. And then gradually we can find out in 2017, these things become scaled up to 50. And year by year, they become 128, and even in IBM, they expected this year that we covered in 400, but eventually got around 200 to 300, but still a large number. And back to the topic, if you want to do the quantum machine learning today, can I really access this quantum machine? The short answer is yes. So IBM actually offer a 5-qubit and 10-qubit machine for few access. Okay, under this background, we know these things really converge from hardware progress. But why we have to doing this kind of research at this moment? So this coming from a perspective called the noisy intermediate scale quantum. That means right now when we do this computing, we're actually in the acoustic world. And there is some desert, like if you want to directly using this quantum machine. And here is some wall we we couldn't directly go with because it's hardware constraint. But it's possible after this desert, you can just try to implement some preliminary result on the machine, for example, with 10 or 20 qubit and demonstrate, okay, this algorithm can potentially good when the hardware even gets scaled up. So here's the philosophy here and why we should do this hybrid acoustic and quantum algorithm at this moment. Another thing support this philosophy is actually coming from Google's AI blog in 2018. So they also have an idea saying here we have different numbers of qubit. If we really have like saying 10,000 qubit, they are used for an error collect quantum computing. And right now we got around from 10 to, I would say, 1,000. So these things is right now we are needing the near-term application. So saying if we're doing research here, eventually we gotta have big impact here. And that's why and the reason we're doing the quantum machine learning research at this moment. And we have example for speech and language processing. There's actually more discussion, but since this is a taster, I will like to motivate people working on this problem. Like the problem could be is quantum advantage is a right goal for quantum machine learning. Saying we do know there's some quantum advantage, right? So like Google's paper, they can resolve the traveling salesman problem. But meanwhile, in the quantum machine learning, people are really look at is to search a quantum perception, saying what kind of quantum machine we can get, and once we get a certain computable quantum machine, can we design neural network or a quantum circuit? Quantum circuit, that means a tensor network, and which is trained like by gradient shifting. I will cover later. But how to design those kind of heuristic architecture is one open question just right now. And the second part is to have this connection between quantum circuit and general learning theory. So this is something Jun just covered. And third part, I would say, is more something I like because quantum is not the focus of my thesis. So the thing I'm much familiar is like to support some quantum hardware and like to implement some quantum application as a taster. So I would say these three questions are all important, and then it depends on how your expertise and your interest to develop your research align one of this mainstream. So yeah, so in this paper, they actually justify, okay, saying in some way the kernel learning is similar to quantum computing, and I will now cover the detail. You can look at this paper. All right, so that's some take-home message before you fall into sleep. So I would say, with the rapid development of quantum hardware, understanding and design new quantum or quantum-inspired algorithms is an emerging issues. And second, near-term quantum algorithms could be the current goal running on near-term quantum computers. I would say you can consider you can do some toys, speech and language processing with this hybrid algorithm, but potentially once you find out some new combination or some architecture design, they can be really impactful. Like the early year, people can design ResNet or just temporal convolution and get a really good impact to the community. They are not trivial work because this diagram and the representation are quite different. And finally, I would say quantum machine learning has different goals from its theoretical perspective to application. It depends on why you want to combine this analysis. And right now, its theoretical analysis is basically bare and almost empty. All right, so after we have this background and knowing we should focus on this near-term intermediate quantum algorithm and what kind of quantum machine learning we do have, like before the term calling quantum circuit learning, and why is quantum circuit learning and why we're gonna select this quantum circuit learning currently. So let's look at some work before, saying 5 years ago or even 10 years ago, mostly right now. So before like in ACL 2020, 2013, 2017, there is still some attempt to use quantum computing combined with natural language processing. But their main idea is to improve sample capacity when you do this kind of quantum simulation during the language modeling. For example, the token and the sample trying to compute. Another thing is trying to model in the turn dependency with quantum language model. So we'll cover these things, but their idea is not to running these things on your machine directly, but in the algorithm itself, trying to reduce the sample capacity. For example, quantum modeling for both single or compound terms as a density matrix. Density matrix is one kind of mathematical formula in the quantum machine. So their idea can be, I have a single sentence representation once we have some sentence matrix like this, and then we can have our product to product these things is a density matrix. So density matrix is computed in a quantum format. You can think of the include some complex value, and then you can put this sentence matrix at the outer product, and then to have a general representation when you do the convolution in your network. So here you can see this is actually inspired by quantum, but not actually have to run on the quantum machine. The main idea is they use the density matrix to get some complex information. So this is paper published in III 2018, which achieved a state-of-the-art result for compound modeling. Meanwhile, if we look at the newspaper in ACL 13, the idea is trying to have a compositional model, which is also quantum to reduce the opacity. So we can find out they are not focusing on gradient propagation-based training and learning, and there are also pros and cons to avoid. But eventually, we can see by directly imply quantum in those kind of algorithms, simple capacity is something we can really focus. And more recently, this quantum-inspired algorithm. Inspired means like the algorithm not necessarily running on the machine. They also have good result on some acoustic tasks like image classification. I will highlight one work in CVPR this year. They call the image patch is a wave, face-aware vision MLP. So their idea is to have a multi-layer perception, which is an MLP. But between this layer norm, they will have a process called a token mixing. The token mixing will simulate this input token with amplitude as a phase, and then they will have a phase-away token mixing as a wave function, and eventually the output will mixing from the real part and the imaginary part. This is something interesting. Like this process can be eventually run on a quantum machine and get on speed up. But right now, even on CPU, you can get this thing compute directly. The output you got is the outcome you got actually is a better representation when you do this MLP training. And their result, I think, is on the open benchmark at least for 2 or 3 months and better than the swing transformer. Okay, now we see there is some solution with quantum-inspired algorithm. But what is the quantum circuit algorithm which are yet covered, and how we can apply this quantum circuit algorithm with hybrid acoustic and quantum machine learning. So the background about variational quantum algorithm is like this. Variational quantum algorithm, that means like the training progress associated with the variational training process. The variational is not directly related to the variational inference in the scientific community, but I will illustrate later. So there's actually different optimizer before this quantum circuit training coming up. Basically, you can think a problem like this. So I have some theta, which is a trainable parameter here, and we mapping this theta to a tau, which is a quantum computing operator here. And then eventually you can get your actual value and the optimized things you want to optimize. And then you just compute a loss function with gradient as a acoustic algorithm. But here we don't have like graphical connection, right? So one thing we can really do is to add a small perturbation in your input and output to have this gradient shifting. And then you can have these like shifting based gradient update and when we train this algorithm. And the drawback is, it's not broad propagation. The comparator is not really good, but you can still do the end-to-end training. So there's 3 different ways consider this end-to-end training for quantum circuit learning. So the first one called the simulated annealing. So the idea is you have a fixed weight by you trying to minimize this weight times your functions by your algorithm. So you're trying to minimize these things by finding a theta here. And the second is the echo state network. So you have a input, which is a chi0 and over some quantum machine, and you can see there's a fixed parameter. But here is you're not going to find this theta here. You're going to find a weight matrix here. And finally, they call these things like a neural network, which is a quantum circuit learning, QCL. You still have a chi0 here. Chi0 is like you have some acoustic data and with some quantum encoding, you mapping back to quantum space. And you go over one circuit and another circuit. So eventually you can try to have your loss function about your original F and your another quantum circuit which controlled by your theta here. But what is the quantum circuit here? You can think of in neural network, we do this feature mapping. But in the quantum circuit, there's actually a vector in the high dimension space. But this theta just control this vector to mapping to the right direction and eventually have a low prediction loss. So the first one, as a conclusion, is minimize the output of the quantum circuit. And the second one is tuning the weight. And the final one is tuning the quantum, the circuit parameter. So that's why these things is similar to neural network, right? So we have something to control as entirely with the theta. So I would say the first work consider this format as a neural network and training with quantum circuit is from Cohn, ETL, and their collaborator. So their idea is once we have the input of image data, they do the convolution and do the pooling and do the fully connected again. So this paper is actually got really high impact since it published in 2018. And then if you turn out this process, consider with quantum circuit learning. So in the neural network, we have this connection. And in the quantum circuit, there's something similar by winding these things together. You can think of this just a special component, which is similar in the neural network. So for example, this component can be used for pooling your data, and this component can be used to make this convolution. And eventually, you can do another operator for fully connected, and finally, you got the output. So here is kind of measurement. So one thing here, I will say how this quantum-based layer construction eventually make a quantum enhanced transformer. So first, I want to talk about our work with June together. And this work is actually during one of my holiday back to Taiwan. I meet my friend, Dr. Samuel Chen. So he has some issue to write some reinforced learning code. And I just helping to write the reinforced learning code. And he told me this time he didn't use the neural network layer to optimize the loss function. Instead, he used a formula like this. You can see here the R is kind of rotation gate. And R theta 1 and phi 1 is those kind of rotation to mapping your acoustic state value to the quantum space. And then you have a R alpha, beta, and gamma. Those things represent the general single bit unitary gate with 3 trainable parameters. So here the trainable parameters is alpha, beta, and gamma. And then you just trying to rotate this angle and eventually train your model. In this turnout, you only have a few trainable parameters, but you can still do this high dimension space mapping from your acoustic to acoustic data to your quantum data. And reinforced learning is exactly a good playground because reinforced learning will only have a really small state data. And the whole thing you want to optimize is just your reward as a one bit, so one digit thing you're trying to optimize eventually. And once we know these things, actually just replace some layer in the acoustic neural network, like the dense layer. So in the ICAST 2022, there's a paper called The Dawn of Quantum Natural Language Processing. They just take this idea to make this layer. We all know, like in the transformer, we have a key, current, and value, right? So now we can actually define for a quantum circuit here. And by having this embedding and have this entangled layer and have this like trainable rotation gate as I just introduced, and you define this thing as a basic layer. And each time when we compute key, current, and value, you just code this layer, and finally the things will be trainable, and you can have your quantum transformer as a result. So the fact, so now we know these things can be trained perfectly with your quantum machine learning, and you can construct these things with a layer. Although the layer is not ideally understand as a neural network layer, but it's something trainable and can be trained with the gradient from an end-to-end fashion. But there is some bitter lesson when we do this kind of research. So even acoustic to quantum encoding process actually take exclusive time. For example, you want to train a 60,000 mean samples, they will take usually 500 to 700 CPU hours. So usually these things take 20 to 30 days to complete one experiment. If you want to train these things by gradient fully. And the gradient shifting algorithm, I mean, because we don't have the backpropagate on this black box, parameterless black box, right? So you have to use gradient shifting, and each time you get some shifting parameter and to find out your gradient. So these things you will even take longer if you do this iterative training. So after knowing this fact, which constrained by the current quantum machine, because we're doing the CPU-based simulation, could we actually have some options saying, can we skip the training time, but only have this quantum acoustic to quantum mapping? So here's come to the idea. I would say is the economic solution. So this time they introduce a random, which is a non-trainable circuit learning. So each time, once we have a data, like if you're familiar from signal processing, we do the convolutions. Actually, we pick out a n by n kernel, and the n by n kernel while trying to compute with some weight matrix. But why not we just using a random circuit, which the theta of this gate is random initialized, but we only take advantage of this random mapping, but this mapping will be happening in the quantum space. This paper in the Quantum Machine Intelligence in 2020, they find out if you just apply a random initialized quantum circuit and you don't train this quantum circuit and just use it as a random feature structure, you can still train a model and even perform better than the 2x2 neural network kernel at the same time. So their idea is like each time this window will go over input data and to form a computation diagram like this. So the output will generate these things called a quantum convolution. So you can control your channel output. And then the pooling convolution, the pooling 2, and the fully connected are all made by the neural network. So the only thing you take advantage is this kind of representation, mapping by acoustic to quantum and mapping from quantum to acoustic again. So from their result, you can find out compared to CNN, QNN, and random initialized QNN, you can find out the performance is actually much better compared to CNN-based solution directly. And the QNN and random QNN, in some cases, the performance is even similar and as this kind of result. So after finding this paper, the intuition is like, can we apply for speech? So I would say I thank my advisor, Professor Qinghui Li, to let me try these things. Like at least we tried for 1 or 2 months. And our idea is trying to, okay, can we also consider feature extraction for speech processing? But I get a good advice from Professor Li saying, if you directly do the feature extraction, they didn't take any quantum property. Then we just reanalyze this problem, and we find out the problem for quantum computing is you can allocate this quantum feature in another instant. For example, when we do the feature extraction, you can actually put it on the cloud, and the local model they use in other features. So here is a summary saying the overall machine learning approach and really key components. For acoustic model, you have input as bits, and the learning model is DNN and something else. And the output is also bit. But one thing for hybrid quantum model is the input speed, the output speed still, but you in the intermediate layer, you can put something for quantum, and you can put it in the different instance for the security issues or privacy preserving issues. So finally, property is accessible quantum advantage over the vertical filter learning. All right, so it's motivated from to the same things on the data protection, like the GDPR or CCPA. So then the computation diagrams like this. First, we have a local user, and we put this quantum convolution on another instance, for example, IBM instance on the cloud. And then you just the local user will not have like, we will not have this, the feature from the local user, and the local machine will only, for example, your cell phone only have the decoder feature from your quantum encode results. And then you can do the continuous speech recognition or the speech command classification. And we also, as a first work, we should be responsible to analyze this result. We find out from different channel of this quantum compute like layer, they actually learn different representation from high frequency to low frequency. So these things are render initialized, is not even trainable. So which is surprise to us. Another thing is like compared to 2x2 neuron convolution based encoded, like the quantum convolute encoded is actually have a similar representation, but this thing is really sensitive to the window size you select. Another thing we find out, but we didn't put in the paper, is the training time. If you want to train the model, it's not render initialized. For example, you want to train this 4QE based model with TensorFlow. They're actually much stable because you have least trainable parameter, which is more intuitively. Right, so after that, like Professor Chao also applied another work following our work. So in our work, like we put this the quantum convolution as a feature encoder, right? But you can also apply the pre-trained model like the BERT model, and you can put this quantum convolution things as a decoder between you put into the classifier. So their idea is to apply quantum temporal convolution. And then, for example, for each time you have an input sequence, you can just compute these things in one-dimension kernel, and then you can do the global max pooling to carry a final feature. As I say, it's early age, and they are blue sea. They don't even have a quantum temporal convolution yet. So this work also got accepted to ICAP 2022. So now we know like feature extraction is one mainstream for computation perspective on the some early taster for speech and language processing, and there's a lot of following work from the paper in the ICAS 2021, and yeah, I know the Ping An Bank, they even publish a toolkit to do this feature extraction, but I will cover it later due to the time constraint. But I would say like once we know the feature extraction is good, but if you look at the performance is not improved a lot, right? So you got some improvement, but the improvement just 0.0 something, and the maximum we got after cost validation is like 0.1 or 0.8. Another thing I want to deal with is like we know the hybrid model can give some performance-based improvement, but I would say the main property is still the property come from the quantum, you know, like the data isolation and the security reason. So another thing people look at the near-term quantum NLP is to use variational circuit to model in grammar construction. So that means in the acoustic compositional language model, we have this relation like compute by some computational operator, but you can only use these things you can also use a quantum circuit to compute this relation. So in their work, they are defined a variable of Alice and Bob, and they are both variable both by the quantum circuit. And since they are pure quantum like model, so you can do this computation pretty fast in the compositional level. For example, the black hat, you can model in these things with a relation like this, and then you have your quantum circuit to model in this black hat, and you can separate these things with hat and black by two notation in the quantum circuit. So for detail, you can look at this paper from Cambridge Quantum Computing. But they find out you can actually use this computation logic to do a neural computational model and to have a SOTA result, and they release their code and implementation. All right, so finally, I will talk something on the quantum kernel learning and give some basic here. I think as the previous discussion, like the effective of quantum circuit learning based on the Robert Huang's like Nature Communication paper in 2021, and here is the following paper gave a more concrete idea like how we can compute these things in practice. So for kernel learning, now it's not a fancy term, but we know the kernel just trying to separate the data, right? So for example, we have two groups of data. They are, in this case, they are in the plural classification. But we know it's pretty hard to find this real separation from the blue and orange like this. But ideally, if I have a kernel in the high dimension space, we can actually separate this thing properly. But how to design the kernel like that and how this kernel relate to the quantum computing? That's something I'm gonna cover in this 5 to 10 minutes. So in the linear classification, we actually trying to have a hyperplanar, which is controlled by the weight here to separate this two group of data. So with a vector W here, which is orthogonal to it. So for example, we can assign a cluster label Y to adapt a data point like by this. So it's a classic format about support vector machine or regression-based prediction. And then once we have a W plot living in the feature space corresponding to a feature map, we can write in this format into here. Here is the inner product of the two vector. So, but the optimal decision boundary about the equation 2 can be actually compute of a sum of the embedding data point of the real coefficients, which can be computed by this term. So we can rewrite this term by the ratio of alpha and times to this phi xi and phi x. So this term is actually something we can model in by quantum kernel. For example, the quantum kernel just mapping something from acoustic to quantum, and we can have a kernel like here, and to mapping our data from quantum to kernel to find our ideal space for separation. And here's the idea. So you can have your embedding, and finally, with this kernel embedding, you can make your decision eventually. And I think following some discussion later, so this norm is important, but here is a general format. And how these things computing in the quantum space, they have some details. You can refer to this paper. They give a really good instruction and step-by-step derivative. All right, so after find out these things, in the summer, we find out after I done my main work in Google, I still have some bandwidth. So with Dr. Bowley and Yu Zhang, we also tried out, can we use the quantum kernel learning to deal with some low resource speech classification? And I got some a lot of suggestions from Professor Lee to refine this problem. So the problem become once we have a low resource speech, we can pick out some acoustic feature, and then we do the quantum circuit based encoding again. And these things will have some distant matrix measurement by kernel. And then once we have a kernel learning, we can apply this kernel matrix learning and to separate this space with the kernel. And eventually we can see if these things can get a good result. So for this part, they can actually compute by the quantum space with tensor TPU-based simulation, which can accelerate this computation. So we find out interestingly, first we just cut out the Google switch command for the classification. We find out if we deduct the data down to 5,000 K, the kernel-based projection actually perform better than some quantum convolution-based algorithm and the pure DNN and the kernel matrix learning. And these things can be even good for some low resource language we collect. For example, those languages are smaller than 1,000 utterance, like Georgian, Kovacic, Lithuanian, and Arabic. And one thing I find out interestingly, which you can also find out from Robert Huang's paper. So in the quantum kernel training, for the training and for the training apples and accuracy, they are similar to the DNN. But for the testing, in some sense, they will perform better than DNN, and the result will be really stable because they have least trainable parameter. So I will give a link to how you can train these things with MNIST. But there's something we find out is if you apply quantum kernel learning, the standard deviation about train your low resource data will be much small. All right, so now we know the quantum kernel learning is another alternative, like compared with feature instruction-based training. So in ICAS last year, people from computer vision also applied this idea, saying we can model in this diagram by a kernel correlation loss, which is acoustic loss for some three-dimension computation, three-dimension computer vision. And then you can model in some complex things like in 3 dimensions with your quantum circuit. That means you can have a phase information here, and when you use quantum circuit to form your kernel and then do the kernel-based training. So you can find their code implementation here from the Cambridge University. And here is some result. You can come in and make these quantum kernel for optimal transfer perspective and to calculate MMD loss. And finally, yeah, I think as the previous discussion in the first section, in Robert Huang's paper in Nature Communication 2021, right now we are in the early stage doing this quantum applied machine learning. I would say quantum machine learning for speech as application or language as application, no matter how we code it. So we should have to refine our problem, right? As the beginner of this slide is like, what kind of problem you want to do? You want to do the hybrid machine learning or just to see some preliminary result for speech and language processing, or you want to do something capacity based issue to dealing with this key problem in the theoretical computer science issues like the traveling salesman problem. So right now the things quantum machine or quantum computing can really have this advantage is not here. It's like here is those problem quantum machine quantum computing can only deal with, and here is the acoustic algorithm can only deal with. But what potentially we can do is something here. So how to refine the problem can be really tricky. For example, this thing is called a bounded probabilistic polynomial problem. So if you look at his paper, he have a lot of discussion on that. But if you properly refine the problem, like the kernel problem, which we can borrow from this quantum kernel mapping and then use acoustic prediction to resolve our problem, we can actually to have result like this, right? So for the best acoustic algorithm, gather performance like from point A to point 6, but with the projected quantum kernel, you can borrow this theoretical hypothesis from here to have a good result and a much stable performance. So for the result, you can also see this Google AI block. And for the slide, I think I put the slide in the chat. And finally, I would say there's still some open problem. Like the new RIPS last year, people consider, because the kernel learning, we don't have the nonlinear activation like the neural network, right? So people are still considering some feature encoding before the variational measurement. So they can go beyond this kernel learning and to have this high dimension modeling with this feature encoding. So this is the paper from Leiden University. Another thing is like Jun's work. I think he connect this theoretical analysis as the first time to use tensor trained neural network to add this linearity and then to analysis how what's the loss component can affect this kind of tensor to the quantum circuit based training as a regression problem. All right, so that's the conclusion. So for both collection algorithms and data are very selective during this near-term quantum area. I would not say quantum is everything, but if we carefully select the problem we want to work on, they can be really impact. Like 10 years ago, you work on DNN. And when the large prediction model, for example, GPT-3 are available, combine VQC with hybrid model with acoustic combining VQC-based hybrid model with this acoustic pre-training is an open problem, and LLC they'll become even more important. And on speech and language classification, VQC learning right now is showing some preliminary advantage on the sample capacity. For example, you have least trainable Rosie gate and the representation learning just slightly on the design use of that. But I would say if we really want to have a groundbreaking like news for a speech community combine quantum machine learning, how to select a problem you can publish to Nature or Science is important. For example, if you have infinity decoding, can we use these things? And right now, I think this problem is quite open. And I was thank all my collaborator and doing on this related work. And actually, this work is not in my thesis, and I just support these things as a programmer at the beginning, and gradually learn by working on these things, making my hard-handed dirty. And I want to thank Junqi to leading me on this a lot of theoretical work. Professor Qinghui Li, at his age of 70 and still hardworking with us, like learning this quantum machine learning. I know, like in the first ICAS paper we published together, we exchanged email like 70 times when we were trying to revise this term. And Dr. Ping Chen from IBM Research to providing some computational instance. And Dr. Samuel Chen to initiate and let me know the quantum. Dr. Xie from Foxconn Quantum, and Professor Marco, and thanks my mentor in Google, Bolli, and Yu Cao from Academic Synca. All right, so hope you enjoying this talk, and I also have some GitHub resource for you. For example, the QCN for speech, and the following work from Ping An company. They have a work in the IJCN this year. They have a low QP quantum speech application tool, and Jun's work on the tensor train network at variational quantum circuit. And the tutorial from Pennyline, which is a hot AI company for quantum machine learning. They provide a PyTorch-based solution. And the TensorFlow Quantum, you can find a lot of tutorial here. And here's a reference and more reference. And yeah, hope you enjoyed this talk, and I'm happy for any questions. Any questions?
Hello.
Yeah.
Yeah, hello, Huck. Thank you for an excellent tutorial. I have a question about the application of quantum kernel machine on on speech classification task, on low resource speech classification task. And do you have any insight why quantum kernel machine achieve better performance? Is it just simply because it has less tunable parameter? Because if this is the case, you can always give your deep neural network less parameter. So I want to know, are there any insight why quantum kernel machine can achieve better performance on low resource cases? Thank you.
Yeah, it's a really good question. I think in this disentangle measurement, in this distant measurement progress with kernel. So they actually use a relabeling progress on the in the quantum space. For example, they are relabel this speech data with some quantum label, some quantum labels. So these quantum labels help this kernel to separate this data in the high dimension space. I think this is one reason. Another reason is if we really look at kernel-based matrix learning, there's a paper in SLT, I think last year, 2 years ago, they actually used kernel matrix learning outperform DNN-based solution. So I would say kernel matrix learning is already a good candidate model or a good candidate solution for separate this low resource speech comment. And then our idea is like, can we benefit on this kernel to make this kernel much advanced? Yeah.
I want to add something. Okay, so I want to add something new. Maybe it's from my research work. I found that if we use quantum kernel learning, it has a better representation power than the raw feature. So this means that you can use much less model numbers. With a small set of deep learning model or with other models to train to get a well-trained model. So maybe it's I think it's the representation capability for quantum kernel learning. Just Hong said, maybe it's because of more larger representation power, you can use much less model parameters. to get as a military model.
Yeah, thank you very much for provide this idea. So which paper are you referred to? You say quantum kernel model have better representation power. May I ask which paper are you referred to?
Maybe it's a send an email to show. Maybe it's a Caroline, I forgot it.
Okay.
Okay, I'll send an email to show this representation power.
Okay.
I say both vacancy model and quantum kernel model, they has a quantum advantage about their feature representation capability. So if we use other communication, do some classical communication task, maybe it can significantly reduce the model size.
Thank you very much. Thank you.
Yeah, it's a really good question. For
the feature. Okay, the feature becomes more discriminative in the heritable space.
Yeah, and for the matrix learning for keyword spotting, I put that paper there. I think in this paper they suggest an idea for the matrix learning, like the non-parameter tree, like training for keyword spotting. Yeah.
Thank you.
Any other questions?
Yeah, actually, I'm really kind of freshman in this area, quantum machine learning. So may I ask a few questions.
Welcome.
The kernel. Thanks. So kernel learning, where the quantum mechanics or quantum mechanics enters into the learning process is the kernel, right? When you represent the kernel, you use the quantum quantum state. That is, you basically insert that into the kernel, the kernel trick. Is that right?
Exactly.
That's
yeah.
Okay. All right. Cool. So, and then is there a okay? You also mentioned the transformer, particularly the swing transformer. Do you use the some properties of quantum mechanics to compute the transformer, or you're making a specific form of transformer?
I think it's a good question. Maybe I just talk too much. Sorry, talk too fast, like during that part. So if we look at this paper, so which is the image patch is the wave, phase aware vision MLP. So in their work, they just modify this MLP. I'm not sure. Are you familiar with the MLP architecture? What is their perception?
Yeah, somewhat.
Right.
Yeah, I'm kind of familiar with the transformer, the classical version of transformer.
Right. So the main idea is you can see the orange orange block here. So they are associated with the token mixing progress. So this token mixing progress will associate with the PATM progress. They call these things phase aware token mixing. So here they associate this quantum computing progress. For example, they are mapping this input with some empty phase, and they will do this mixing from the real and imaginary. And I think from their architecture, all right, so
the quantum mechanics enters into the transformer through like the KVQ, the computation of KVQ. Is that the part?
Right. So here they are all token about KVQ, right? So you can think of this KVQ are all going through with this token mixing progress from this input. So in the VIT, you put this input as a token, but before you fit into your MLP, you actually can get another features like from this mixing progress.
Right. Actually, because you basically replace the inner product, classical inner product, with the quantum mechanical inner product, right?
No, exactly. So here is the original patches you're feeding to your like your transformer, like the MLP here, right? So if you ignore this progress, you just directly feed your token here. But here is just like you do some token mixing, and after the mixing, you give this new token to your transformer. Yeah.
Okay, so the quantum mechanical computation is performed before it enters into the classical transformer.
Exactly.
Right? Okay, I see. Okay. What about the during the computation of the transformer, because it is in a product, right? I mean, can you replace it with the quantum mechanical computation, because that isn't also in a product, right? Would that do anything?
It's a good question. I think this paper mentioned how to do these things called a quantum attention. So from this this paper, there's following work called quantum attention to reduce the sample capacity, but due to the time constraint, didn't cover here. Yeah, there's another way to introduce this quantum-inspired computation for transformer-based algorithm. Here, I select this paper. It's one of the SOTA result on the ImageNet. Yeah, classification. Yeah, it's the I think it's the SOTA result for 2 or 3 months. Yeah.
Cool. That's great. Yeah. Thanks so much. I have another question. So adding the nonlinearity. Yeah, I was actually